In Chapter 7, we are going to discuss first-order circuits. Specifically, we are looking at the transient response of these circuits, which are circuits that comprise of either a resistive and capacitive component, called an RC circuit, or a resistive and inductive component, called an RL circuit. So what we mean by transient response is the response in time. Okay, so we've done steady state response so far, and that's when the response is fixed in time. That includes either the DC portion of a circuit operation or the AC portion that is sinusoidal. Okay, so either of those we mean steady state. Transient means changing in time. So when we are showing an RC or RL circuit in the time domain, looking at the transient response, and those circuits will be characterized by a first-order differential equation in this time domain. So there are two ways to excite first-order circuits. One, we could charge the reactive element, which is the capacitor or the inductor, such that there is an initial condition that is non-zero. So we're charging the element if it's a capacitor, charging that electric field. So that's just by storing charge in the capacitor. And an inductor, we're charging that magnetic field by putting alternating current through the element. And in either case, we charge it to some initial condition. So with a capacitor, we're worried about the initial voltage. For the inductor, we're worried about the initial current. In this case, we call this source-free. We don't have a source at all in the problem. The capacitor, the inductor, is temporarily going to be supplying power. And this is called source-free or natural response. And this initial energy that is stored causes current to flow through the resistive network that gradually dissipates. And two, we could apply the RC circuit to an independent source, thereby forcing the response. So we call that forced response. So we can actually derive the general response, which will be the summation of the source-free and the forced response at one time, and so that we will take these two cases as special cases. So the book is going to spend a few pages talking about source-free response, a few pages talking about forced response, and then put those together in what we call general response. I'm just going to derive it one time, and then we'll show how these are special cases. So there's really only one method to remember here. So what I'm going to do is I'm going to take a basic RC circuit. It's just a single resistor and capacitor, and call the voltage across those, since they're in parallel with one another, voltage V. And I'm going to assume that the initial voltage at time equals 0 seconds is some fixed value, capital V naught. So I'm assuming it's charged up initially to some DC value, V naught. And I'm going to derive the current that flows through this network, thereby finding the final output voltage V as a function of time. So in doing so, what I'm going to do is use nodal analysis. I'm going to make this bottom node ground such that I'm going to assume that I have current leaving the node on both sides. We know that the current will be going in one direction, actually. Positive current will be going in one direction around this loop, but this just makes the analysis, the derivation, a little bit easier. So I'm going to do a KCL at voltage V, or at node V rather. And I see that would be the current through the resistor, IR, plus the current through the capacitor, IC, equals 0. Okay, now subbing in the IV relationships for the current through the resistor, that would be voltage V minus 0 over R. The current through the capacitor is C times the first derivative of the voltage across the capacitor, which is V minus 0. So C dV over dt equals 0. Okay, rearranging a little bit, I can write dV dt equals negative 1 over RC times voltage V. Grouping the voltage terms together, I get dV over V equals negative 1 over RC dt. To get rid of the dv and dt terms, I'm going to integrate both sides. The integral of 1 over v with respect to v is the natural log of v. And the 1 over rc term is constant. I have the integral of 1 times dt, which is going to be t. And I'll have an integration constant k here as well. So what I'm going to do to simplify this is I'm going to let this integration constant equal the natural log of a, some constant a. I'm going to put it in the form of a natural log to mimic that on the left side of this expression, and it'll help us solve this problem a little bit simpler. And if I do this, I'll have the natural log of v minus the natural log of a, moving that k term over to the other side, equals t over rc times -1. Okay, I can get rid of these natural log terms now by raising both sides of this equation by an exponential power. So this can be rearranged as e to the natural log of v over a. When I subtract the natural logs, it's like dividing the coefficients, or dividing the terms rather, equals e to the -t over rc on this side, and the e cancels with the natural log over here, and I get v, which is a function of time, equals a times e to the -t over rc. Okay, so we derived that the voltage as a function of time is going to be an exponential with a negative raised to a negative power times some value a. We can solve for what a is in this particular case by remembering that we were given an initial condition that v at time 0 equals voltage v sub 0. So we can take this expression and sub in that time equals 0, so we get a times e to the 0. E to the 0 is 1, therefore a just equals v sub 0. And our final expression is voltage as a function of time is v naught e to the -t over rc volts. Note that this would be what we called source-free response because we didn't have a source given in the problem, and we initially charged the capacitor up to voltage v sub 0. Solved. Then I should also note that for an RL circuit, we can do a similar derivation, and we're going to solve for the current through the inductor, and we'll get an expression that looks very similar, but it will be in the current through the RL network will equal an initial current I sub naught times e to the negative R over L times T amperes. One thing to note here is that we can make this expression a little more generic, and in both cases we could write, say, v as a function of time equals v naught e to the -t over parameter tau, or I equals I naught e to the -t over tau, where tau is the decay time constant of this exponential, and depends on whether or not we're dealing with an RC or an RL circuit. For an RC circuit, we see that tau just equals RC. It's a unit of time, and we've mentioned this in past lectures. And for an RL circuit, tau equals L over R. So based on that derivation and interpretation of the final equation for the voltage or the current through the RC or RL circuit, we see that given an initial condition, which would be a voltage for the case of a capacitor or the current through the case of the inductor, that voltage or current decays given the e to the -t over tau term, and it decays exponentially when connected to a resistive load. And again, this is what we mean by natural response. So if we're look at v as a function of time, initialized at v sub 0, will decay towards 0 at which point all of the energy that was initially stored in the capacitor has been dissipated by the resistor. And for the case of the inductor, that will just be I naught, and we'll be plotting I as a function of time instead. A couple of rules of thumb here to point out that I think are useful when analyzing this. So this curve is what represents the function a e to the minus t over tau in either case, where a is v naught or I naught depending on whether it's an RC or RL circuit respectively. It's sometimes useful to find out where tau is on this curve, and in general it's going to be somewhere about right here, where that's either going to equal RC or L over R, depending on the type of network it is. It turns out to be roughly 0.368 times the initial condition. So just over a third of the initial value is left over at value tau. The other thing that's useful to note is that since this is exponential, it technically never reaches zero. Never decays out completely. So oftentimes what we do is we assume out at 5 tau we are back in what we call steady state again. In other words, after 5 time constants, we assume it's close enough to decayed out to 0 that we assume it's 0.